So I'll talk about the degenerate special Lagrangian equation. And in another sense, this is going to be the geodesic equation for a certain space of Lagrangian submanifolds. So, yes, really what I'd like to do is sort of motivate why one would want to study this equation, and then towards the end of the talk, say what little is known. And the motivation I have for today is essentially there's two things. One is sort of uniqueness and perhaps existence. For special Lagrangians, not degenerate ones. And the second motivation is actually sort of more dynamical. And so just there's a way of thinking about the Arnold conjecture via such guise. And this would be the sort of strong version. And then, well, there's the sort of known results, which I think I'll only have time really to discuss what's known about sort of looking at graphs in CN, graphs, Lagrangians. CN. Okay, there's, if really a lot of time, then there's also stuff about matching cycles in AN Milnor fibers. So this part of the talk is joint with Rubinstein. This part, if it ever comes to exist, is joint with Yuval. Let's see. Uh-oh. So to begin with, I just want to, recall basic definitions. So this is going to be towards special Lagrangians. First bit of motivation, which is why I first came to think about this. So suppose we have a Kähler manifold. So here, as a multi-geometer, I think about this as symplectic form. This is a compatible, not almost, real complex structure. And then there's going to be an additional piece of information making this basically a Calabi-Yau manifold. This is a holomorphic N0 form, which vanishes nowhere. And I'm going to assume for simplicity, this is not really necessary, that this is actually a Calabi-Yau metric, so that can be written as say this is so C here is some mysterious constant, which is generally taken to be something like this. This is not important. So, example, which will be the main example later in the talk, is we take xcn omega, usual symplectic form, and big omega, just the product of the dz's. Okay, so this is the Calabi-Yau condition. Right, so what do I mean by the metric? So of course we have, as usual, G is defined by J and omega, so then this means that G is a Calabi-Yau metric. Anyway, so in this setting, okay, so what should one know about these things? So let's say gamma, suppose gamma is a Lagrangian submanifold, then it's a fact, I guess, discovered by Harvey and Lawson, work on calibrated submanifolds, that if we take omega and restrict to gamma, it's going to be equal to e to the I theta times the volume form of gamma for theta from gamma to S1, some smooth function. Okay, this is the Lagrangian angle. And the special Lagrangian equation just says that the Lagrangian angle is constant. Get out once. If theta is equal to some theta naught. And there's lots of ways of rewriting this. So for example, we can write the imaginary part of e to the I, e to the minus I theta naught times omega is equal to 0. Or alternatively, we can write by what's written above. This is the same thing as saying that the real part of e to the minus I theta naught omega is equal to the volume. Here I mean the volume form induced by induced by G. Okay. And this is essentially a condition known as calibration, which means that that gamma is actually volume minimizing. So among what? So you could say within its homology class if it's compact. Okay. So sort of a question is, let's suppose that we look at the space of Lagrangian submanifolds in, so let's say L is the space of Lagrangian submanifolds. Inside of X. So that we have a action by the Hamiltonian diffeomorphisms of X on L. So if we have a diffeomorphism phi, then we take some gamma and send it to phi of gamma. Okay. Let's go over here. Right, and then let's say O minus is going to be an orbit. So just fix some orbit. Of Ham. And sort of question which people are interested in is, does a given orbit of Ham contain a special Lagrangian representative? So does there exist gamma, and so which is special Lagrangian? So people see this as some kind of stability condition for, so is this orbit of Ham stable in some sense? And you can also ask, if it exists, is it unique? Okay, so there's a way of studying this question using a notion of positive Lagrangian. So, or almost calibrated Lagrangian. So gamma is called, so if it's Lagrangian, it's called positive if we take the real part. Oh, sorry, I forgot to mention over here that yeah, so without loss of generality, we can always take theta 0 to be 0 by changing omega to e I theta 0 omega. And I guess there's sort of an obvious homological obstruction to finding special Lagrangians in a given orbit of a given phase. So I should always assume that so let's take D to be the homology class represented by Lagrangians in O. In O minus. So we should assume that, I mean, this is without loss of generality, again, by switching the phase by constant. We can assume that the integral of the imaginary part of omega on D is 0. Now this makes sense. So we can define a Lagrangian to be positive if the real part of omega restricted to gamma is positive. I should have said here that gamma is oriented. Okay. So first observation is that if we take a special Lagrangian, that means that the real part of omega is equal to the volume form, which is by definition positive. So all special Lagrangians are positive. So if we want to look for special Lagrangians, we might as well just look among the positive Lagrangians. Okay, so we'll just focus on a smaller orbit. Sort of, we look at, okay, so, right. Let's say this properly. Say L plus is going to be just a set of all gamma inside of X, which are positive Lagrangians. So like this, gamma positive. Okay, and then we're just going to fix a component O inside of the intersection of O minus and L plus. So it's useful to note this is an open subset, obviously, because it's just a positivity condition. And so this is going to just be looking for some component of an open subset. All right. Now, what do we gain by focusing just on positive Lagrangians? So I want to understand this space geometrically. The first thing is to think about the tangent space. So if we fix some Lagrangian inside of this orbit of positive Lagrangians, then we can look at the tangent space of the orbit at gamma. Well, that's going to just be the same thing as functions on gamma. Of course, mod constants. And And the first nice thing about positive ones is there's the canonical way to choose this constant. So we consider functions on gamma such that, well, there's two things that can happen. If gamma is compact, I might as well take the integral of h with respect to this positive form and demand that it's 0. And otherwise, I can just say that h has to be compact supported. Or okay, so there's, for each deformation of a Lagrangian submanifold, which is comes from a Hamiltonian flow, I can assign kind of fixed, a unique function. Okay, now the challenging part. No, bad guess. Huh. No. Actually, I have to. Are there any questions while I'm playing with the boards?
This positivity has some relation. In the case of Hermitian vector conditions.
I think it's the same thing as looking at a connection which comes from a Hermitian metric. So, I mean, there are some homological obstructions, but besides that, I don't know how to answer that question. But I mean, yeah, that's obviously the first question one should ask. if you can find a but I think, there's lots of examples. Okay, so, okay, so this is tangent space, and so then we can define a Riemannian metric on O by, so we have to say what the inner product of two tangent vectors is. So we just take the product of the functions and integrate with respect to this positive measure. So for h and k belonging to h gamma, which is the same thing as the tangent space. Okay. And one nice thing about this metric is that it comes along with a functional which is convex with respect to it. So to do this properly, I should go to the universal cover. Let's say O. So this is going to be the space of all maps from an interval to this orbit, such that the beginning has to be some base point. And we should consider such paths up to homotopy. And we can, given a path like that, we can project it down to its endpoint. And that gives us the universal covering map. No. This is inefficient. But so let's define a functional C from O to from the universal cover to R by, so C of some path lambda is given by the following thing: 0 to 1 integral over, so I'm going to write lambda of t is equal to lambda t, and then take ht imaginary part of omega dt. So here where ht is sort of, you just take the derivative of lambda t with respect to t, so that's going to have to be something in the tangent space at lambda t to O, which we know is some kind of function on lambda t. So we can take that function, integrate it with respect to the imaginary part of omega on lambda t, and then integrate the whole thing from 0 to 1, and then there's a theorem which says that, first of all, it's not clear that when we consider different paths up to homotopy that we get the same answer, so C is well defined, so independent of homotopy relative to endpoints. And that's number one. Number two, C is convex along geodesics of the metric. And number three, the critical points of C are basically special Lagrangian submanifolds. So critical points of C, they belong, of course, to the universal cover, but if you then project them down to O, the original orbit, so then this is going to go down to special Lagrangians in O. In particular, if we know that there exists geodesics, then special Lagrangians have to be unique. So it's not really a corollary because we don't know anything about geodesics, but it's just a so. If there exists a geodesic between any 2 points of O, then a special Lagrangian inside of O must be unique. All right. So this story is kind of very similar to something which is going on in Kähler geometry. So there's extremal Kähler metrics. Constant scalar curvature Kähler metrics. So in our story, there's so C corresponds to, well, okay, maybe O corresponds to the space of Kähler metrics. And there's a similar story for holomorphic vector bundles and Hermitian, Einstein-Hermitian metrics on them, but maybe it's a little bit less involved, so it's not as good an analog, but or at least it hasn't been developed as far. So, and then there's a Mabuchi metric on, oopsie, here there's this metric, and then here there's the Mabuchi metric. And C correspond roughly to the Mabuchi K energy. And there's a lot of work which has shown the existence of geodesics for this metric. And use that to prove uniqueness of constant scalar curvature metrics. One other thing which is maybe worth mentioning is that so there's another theorem which says that this metric is non-positively curved. And this corresponds to a theorem proved by Mabuchi, later by Donaldson. Which says that the Mabuchi metric is non-positively curved. Okay, and there's recent works which actually use this kind of setup to actually address the existence problem as well. I mean, it's very preliminary at this point, but because you can show the long-term flow of C exists in some weak sense, at least. Once you know enough about so there's some work of streets, I should mention. That's one piece of motivation. Uh-oh. So the other piece of motivation is the Arnold conjecture. So I guess it really comes down to saying explicitly what a geodesic is. So first of all, what's the connection? So what's the Levi-Civita connection? Of this metric. So in other words, let's suppose that we're given some path lambda, maybe small path, short path, which goes to O. And we're given some vector field along lambda. So say kt belongs to h lambda t is a vector field along lambda. So then what does the covariant derivative of that thing look like? Uh-oh, wasn't supposed to erase that. Whatever. So, right. So to kind of make things more concrete, we have this family of Lagrangian submanifolds which kind of moves around inside of X. Now we have to compare functions on the different Lagrangian submanifolds. So it's useful to sort of choose some kind of parameterization. And of course, the answer we get could depend on the parameterization a priori, but there's a way to do it so it doesn't. So we choose some gt from L to lambda t. It's going to be just some diffeomorphism, family of diffeomorphisms. It's going to make sense of what it means to be smooth because they're just maps to X. So with image lambda t. And then let's let Wt should be a vector field on L such that if I contract the pullback of real omega with Wt, that should be negative the contraction of real omega with the time derivative of gt. This is a slightly confusing notation, so let me explain. Yes, I have one more word. So given if we have a map say from L to X, then and we have a vector field along this map, so a vector field along F, then we define IV, which maps a k of X to a chi minus 1 of L. This is forms by taking some alpha and sending it to so IV of alpha of x1 to xk minus 1 is just sort of alpha of v and df of x1 up to df of xk minus 1. sort of standard thing to do, but slightly confusing. Dear, whatever. So are there any questions at this point? Haven't yet written the definition of the connection, but okay, so the answer to the question of what the connection is, then, so the covariant derivative should be a sort of vector field, again, along this path. So it's going to be some function on lambda t, but I mean, that's inconvenient to talk about, so I'm going to say what its composition with gt is. That's close enough because gt is a diffeomorphism. So this guy has got to be equal to just the derivative with respect to t, kt composed with gt. That's what you kind of expect to get for a derivative of something along a path, but that, of course, is going to depend on gt. So we have to correct it by wt sort of acting on the derivative in the direction of wt of this function, kt composed with gt. In other words, gt star dkt evaluated on wt. Okay, so this is independent of choice of gt. Okay, now to get a better idea of what this means, it's useful to kind of work in a parallel frame, like one does in Riemannian geometry. And this will kind of immediately show what this has to do with the Arnold conjecture. So the parallel frame is given by just sort of choosing the family of diffeomorphisms gt, the parametrization of these moving Lagrangian submanifolds in a clever way, basically by Palar transport. So, so that psi t is going to be a diffeomorphism of L, be the flow of wt. Okay, then we can just take gt and precompose with psi t, and that gives me gt tilde, and well, then it turns out that the real part of omega, when I contract it with gt tilde dt, is just going to be 0. Okay, so that means that when I compute the covariant derivative with respect to, so then the kind of corresponding wt tilde is 0, so then I can just look at the usual derivative. So then dk t dt composed with g tilde is just going to be equal to the usual derivative of kt composed with gt tilde. Okay, so now what does it mean to be a geodesic? I should have labeled that equation. Drat. Oh, well, it's forever gone. Okay. So, geodesic equation. So it now says that basically we should take our vector field along lambda t to be just the derivative of lambda t. It has to be parallel. So explicitly, this means that I dg tilde t dt of omega is equal to d of kt composed with like that. All right. So then lambda is a geodesic if and only if the covariant derivative of d lambda t dt is equal to 0. So that's the same thing as saying that d dt of kt composed with this guy is 0. So that just means that kt composed with g tilde t is constant. In time. So it's a constant function from L to R. So why does this say something about Lagrangian intersections? Or for that matter, fixed points of Hamiltonian flows by extension. Uh-oh. It's coming down. Can't see it. Are there any questions at this point? So that means that, again, that's what to say. So if lambda is a geodesic, then lambda 0 intersect lambda 1, if you take the number of points in there, that's got to be greater or equal to the number of critical points of k. Okay, so proof. Well, let's suppose that P is a critical point of K. So this is going to be inside of this domain for the parametrization. Then we have dg tilde dt of P is going to have to be 0, because we know that dg tilde dt, when I contract it with the real part of omega, that's 0. And we also know that we can contract the g tilde dt with omega, I get dk, and well, if I evaluate that at p, that's going to be equal to 0. And we know that real omega is positive, and this kind of says that the normal part of dg dt vanishes. this is the normal direction of dg dt vanishes. And because of positivity, this says that the horizontal, the tangent direction of dg dt vanishes by positivity. Okay. So as soon as you see that this thing is constant, that means that gt of p belongs to the intersection of lambda 0, lambda 1. So in a sense, what happens is that we say that basically any Hamiltonian flow can be made autonomous in some sense. So if you restrict your Hamiltonian to the actual Lagrangian, which is being flowed along, if you choose your parametrization correctly, then it just becomes autonomous. So I'm kind of running out of time. So you can apply this by the graph construction to, okay, maybe a few remarks. First of all, if lambda 0 is transverse to lambda 1, then k is Morse. Okay, so you can get both information about the non-transverse case and the transverse case if you have existence of geodesics. And furthermore, so you can apply this, of course, to Hamiltonian fixed points. By looking at the graph.
Does it mean that you have two Lagrangian semifolds in Cn is kind of displacing Hamiltonian? There's no geodesic?
Sorry?
I mean, about Lagrangian semifold Cn,
Mm-hmm.
and you displace it by Hamiltonian.
Mm-hmm.
Then these two are cannot be joined by geodesics, right?
So I mean, that's correct. I mean, if you can, but I mean, currently you need some kind of compactness to show existence. So you should have some kind of compact support. So in Cn, it doesn't really give you much in the way of topological conclusions, but at least the results we have in Cn indicate the equation can perhaps be solved. So the graph of phi in times m.
This is saying that a strong version of the Arnold conjecture would follow only for pairs of Lagrangians you knew a priori were positive.
That's correct.
Right.
So you're getting some kind of condition on your Lagrangians, but this is not like C1 small or something like that. You can be very, very far apart and still be positive and connected by positive and stuff like that. It's just some kind of different condition which you can assume on Lagrangians, and it leads to assuming the existence of geodesics, some kind of all right, here. So what do I know about existence? So let's suppose that we consider X to be just Cn with standard everything. so we want to consider, so we have a function on Rn. We can look at this graph. In Cn, which is going to be defined to be the image of some map G phi, where G phi of maps L or Rn to Cn by x goes to x plus I d phi x. So just take the graph. Okay, so I mean the right thing to do is to write what happens in general. You can construct from a Hamiltonian isotopy a certain Lagrangian cobordism, and then you can say that Lagrangian cobordism satisfies some kind of degenerate special Lagrangian equation. I'm going to just do it directly in Cn. So the real part of, so if we take G phi, that's just the same thing as the real part of the determinant of the identity plus the Hessian of phi times I. Okay, so gamma phi is positive if the real part of the determinant is positive. So similarly, if we have U from, say, Rn to R, so then we can look at the family of, so we can say lambda t is equal to just the graph of ut, and then it turns out that so okay, so then we've lambda t is a geodesic of positive Lagrangians if and only if the imaginary part of the determinant of I hat, the Hessian of U, is equal to 0. So here I hat is like this. And the real part of the determinant of I, the x Hessian of U, is greater than 0. Okay. And well, the theorem itself in Yanir is that you can solve the Dirichlet problem for for this equation. So you fix some boundary conditions on your function, and then you can just solve inside on a bounded domain with some kind of convex boundary. So for U is going to map, say, 0, 1 times D to R. D is a bounded domain, convex. It's weaker than convex, but that's enough. And I mean, the thing which says this is sort of nonlinear equation is that so far we don't have much in the way of regularity. So we can uniquely solve the Dirichlet problem of that thing for U on a bounded domain across the interval, and the solution belongs to just continuous functions on 0, 1 times D. If we just assume general boundary conditions, I'm slightly suppressing things because I'm out of time, but we can also get Lipschitz, a priori Lipschitz bounds in the time direction. Lipschitz in T. So that means we can make sense of the time derivative, and meaning and in the convex branch, so there's different branches here which I'm suppressing, but we can actually define the length of a geodesic. So then you have to make sense of this measure, real omega, but it can be made sense of. I guess I'm going to stop here.
So just to clarify, the claim here is that among graphical Lagrangians, there always exist geodesics between points?
I mean, in some very weak sense.
Yeah.
So I mean, you have to make sense of the Hessian, because this is the Hessian equation
Sure.
of a C0 function.
Okay, yeah.
But I mean, this has been done. It's like called a viscosity solution. And I think, I mean, it should be possible to get better regularity results, but just the kind of off-the-shelf techniques which we could find were just to give this kind of solution. And, well.
And I had another question, which is kind of more broad. So I guess complexifying all of this structure, is there kind of a good geometric interpretation of this? Does it get into complex symplectic geometry, or?
Well, I mean, I don't know if there's a story of Donaldson in which he studies Lagrangians and certain twisted cotangent bundle, which are complex symplectic Lagrangians, is what they're called. So I think this story is mirror to that story. So you could think that it's actually, that story is a subset of this story, but it's not. I mean, in theory, one could complexify this just without paying attention to anything. And that seems like it could be very interesting, but I haven't tried to do it yet.
Okay, great. Thank you.
Any question? So the sound speaker again.